Hey, how's it going everyone? Welcome to this video on 13.6. Today we're going to have a look at optimization problems. So to solve optimization problems, basically we're looking at examples where we have a situation um, and we've got a lot of words. We've got to take the maths out of the words and use our knowledge to work out, in this case, area um, and lengths and heights. So that's what we're looking at. So to be able to work these problems out, we need to go through a few little steps. So most of the time, draw a diagram of the situation if it's not already given. It's going to help a lot more to be able to visualize what we're after and what we need to do. Second point is to identify the quantity to be maximized or minimized to define the variables involved. Express the quantity to be optimized as a function of one variable. Find the stationary points of the function and determine their nature. The last one is consider the domain of the function as there are likely to be restrictions in practical problems. So height can't be negative, time can't be negative, etc. And so finding the endpoints of the domain, and then the final one is maximum and or minimum values of the function will either occur at the stationary point or at an endpoint of the domain. So a lot to take in. Let's have a look at an example. So example 12, we've got a new owner of an apartment wants to install a window in the shape of a rectangle surmounted by a semicircle in order to allow more light into the apartment. At the moment, the owner has a 336 centimeter of wood for a surround of the window and wants to determine the dimensions as shown in the diagram that will allow as much light into the apartment as possible. So the first question asks, show that the area A in centimeters square of the window is this nice little big formula. So to start off with, we're looking at area. So the area of the square, and we've got an area of a semicircle. So let's do those individually. So area of the square or rectangle uh, is going to be our base times height. In this case, we've got 2x times h, or just 2xh. And then the area of the semicircle is going to be a half pi r squared. In this case, we've got 2x as r. Um, well, r is going to be half of that, so it's just x. So if our diameter is 2x, then our radius is just going to be 1x. So half pi r squared or half pi x squared. So the total area of the window, so total area is going to be our 2xh plus our half pi x squared. Now, we're not finished here, so that's the total area of the window. The perimeter of the window, so perimeter of the window is 336. The circumference of the semicircle is a half times 2 pi x. So the perimeter of the shape is going to be our height. So we've got 2h, we've got the base there as 2x, and our semicircle, half 2 pi x. So I can say 2h plus 2x plus a half 2 pi x is going to be equal to 336. So if we express that in terms of x, so express h in terms of x. So if we rearrange that and solve for h, we get h is actually a half 336 take 2x take pi x. And if we sub that back into this one here, we get our area is equal to 2x, and h is now this one down here. So half 336 take 2x take pi x plus a half pi x squared. Pretty ugly. If we expand and simplify, we'll get that, and simplify that further, we get and the final step which is what we want. So you might want to have a go at doing that yourself. So it's just expanding and simplifying. I'm not going to go through the exact steps of all that. So if you have a look, we get 336 take a half 4 plus pi x squared, which is what we want. So that's part A. Part B, or question 2 says, hence determine to the nearest centimetre the width and the height of the window for which the area is greatest. So we're looking for when the area is greatest, okay, indicating that we're looking for a maximum turning point. So if we find our derivative of the area function and make that equal to 0, we get 336 take 4 plus pi x, and work that out. When that's equal to 0, we get 336 equals 4 plus pi x. So x is going to be 336 over 4 plus pi, which is roughly 47.05. So as the area function is a concave down quadratic, the stationary point is a maximum turning point. The height for which that occurs, we had 2h equal 336 take 2 times 336, 4 plus pi. Work out that, and we get h is roughly 47.05. So the width of the window is 2x. So we get 2 times 47.05, which is about 94 centimeters. The total height of the window is h plus x. So we get our height, which was 47.05, plus 47.05, which again is roughly 94 centimeters. So therefore the area of the window will be greatest if its width is 94 and the height is 94. And the third part, part C, structural problems require that the width of the window should not exceed 84 centimeters. So what should the new dimensions of the window for the maximum area be? So if the width is not exceed 84, oops, 84, we have 2x has to be less than or equal to 84. So x has to be less than or equal to 42. With the restriction, the domain of the area function is going to be between 0 and 42. Again, can't have negative area or length. So determine where the function is greatest. So the stationary point occurs when x equals 47. For the domain 0 to 42, there is no stationary point. So the greatest area must occur at the end point. So at x equals 42 is going to be our greatest. So if we work that out, we get h is going to be, oops, is about 60. So the width is equal to 2x, which is 84, and our height is h plus 2x. So if we work that out, we get 102. With the restriction, the area of the window will be greatest if its width is 84 and height of 102. So that's 13.6. These questions do take a while, so take your time, leave plenty of space, draw your diagrams, that's the most important part. Ask questions. Thanks for watching.